Hello, welcome to my presentation. My name is Wei Songwen from Hong Kong Polytechnic University. In this presentation, I'm going to present our latest work using 3D LiDAR to help the GNSS-RTK positioning in urban chaos. Here is the outline, includes the background and the overview of our methods and the proposed methodology and experiment results and discussions. GNSS-RTK. The major problem of GNSS-RTK in urban chaos is the NLOS receptions. Only the reflected signal are received. This is NLOS non-left side receptions, and another one is the multipath effects. Here is a typical test using a commercial level GNSS receiver. You can find only a 2% fixed rate is achieved in such kind of scenario. Very challenging, and 10 meters of error in this scenario. Why? Because only very limited hearsay measurements are received. The red one represents the non-left sides, and the green one represents the hearsay measurement. It's pretty challenging. Okay, some solutions are proposed to mitigate the effects of non-left receptions. For example, the building model-based detection and similar work is done here based on very good initial guess. However, all these methods relies on the initial guess of the GNSS receiver to further detect the non-left side receptions. And this is a very famous geometry. It proposed to using hypothesis-based method to detect the potential to mitigate the effects of non-left reception. However, it also relies on the initial guess, share the same drawbacks with the previous work. It relies on the initial guess and the satellite visibility classification. Actually, in urban chaos, the initial guess is pretty hard to be guaranteed to be accurate. This is the ray tracing-based method. It also relies on the initial guess of the GNSS receiver, and also it can cause a very high computation load. In the very recent work, we propose to extend the 3D building model aided GNSS to the GNSS-RTK to see how it can help to improve the GNSS-RTK in urban chaos. Similar concept is applied to GNSS-RTK, and some improvement is obtained. However, it still relies on the initial guess of the GNSS receiver for errors for non-left side detections. In this work, very interesting, researchers propose to using a camera to look into the sky to further detect the non-left side, and some improvement is presented here to using more state-of-the-art sky segmentation method to detect the non-left side. However, all these methods is based on camera. It can be very sensitive to the illumination condition. For example, during night scenarios, it can be very challenging, right? Another method is to using more sensors. For example, using IMU or using cameras. In here, using additional IMU to help to increase the data redundancy to detect to do the auto rejection, to detect the GNSS outliers. And here the camera is applied to generate more data redundancy. However, all this method relies on the assumption that your visual odometry or MU can work pretty well to further detect the non-left reception. However, in urban chaos, it's pretty challenging. It's hard to satisfy this kind of assumption. It relies on the initial guess. Actually, from 2018, we continuously proposed to using the 3D LiDAR, which is an onboard sensor for auto driving, for online localization or offline mapping. It also still use the 3D LiDAR. In here, we propose to use the 3D LiDAR to detect the non-left side caused by the bus. This is double-deck bus. It's a dynamic object. It's very different from the previous work using 3D building model. 3D building model can only involve the static one, but with the LiDAR, we can online mode to understanding what happened surrounding us using LiDAR to detect even the dynamic and the static one. In this work, in 2019, we extend our work to the building detection to detect the building and to find out the potential non-left side caused by the building blockage and reflection. And in this work, we extend this work to LiDAR and GNSS integration. And in here, we relax the problem of in here using single epoch point cloud to detect the building and double-deck bus. The FOV, the field of view is quite limited using single LiDAR. Therefore, we accumulate multiple epoch point clouds to generate a local map. And the FOV is slightly increased, but it's still limited using a single LiDAR due to the physical properties of a single 32 channel LiDAR. It's due to its own properties. This is also presented in ION Plus 2020. So, okay, in this work, we are going to relax some problems in our previous work. The first one is like we're using multiple LiDAR. You can see here, the black, the yellow, the green and the red and the white represents 3 different LiDAR. For example, the green one can generate the tall buildings. The right LiDAR can also generate the puncture from the right side. And the middle LiDAR can generate the puncture from the low-lying buildings. In this case, we extend using multiple LiDAR to increase the FOV. This is the first contribution. The second one is we extend the previous method to the GNSS-RTK in this paper. And moreover, using the GNSS-RTK to further correct the drift from the LiDAR slant to build a more accurate local map to improve the accuracy of potential and loss detection. Actually, this is a very typical sensor setup for high definition mapping. For example, for auto driving, for UAV based mapping, this is a very typical sensor setup. Okay, the overview of our method. The first one is we try to use LiDAR, multiple LiDAR and IMU to generate a local map. You can see the tall buildings can be generated. Therefore, the potential non-life site is going to be detected using the map and the GNSS measurement, and we can do the error detection. For example, red one here is the non-life site, and the blue one is the long side measurement, and the green points here is the online generated local map. It's a representation of the environments, including the trees and the building walls, and even a dynamic object. And after we do the errors exclusion, we can using similar method, GNSS-RTK, to calculate the flow solution. And then we do the ambiguity resolution using LAMBDA. And finally, the fixed solution is applied to the position estimation to further correct the puncture map. Okay, first I will introduce this one, the laser inertial integration. This is actually based on our previous work here. This is the vector graph. Here's the state, and here that's the state, and here's the IMU pre-integration factor, and here's the laser scan matching factor. For more details, we refer to our previous work here, and here the state is represented here. And for each state, we include the position, velocity, and orientation, and the bias of the IMU. And in here, we can derive the residual of scan matching factor and the residual for IMU pre-integration, and a cursive kernel-based auto rejection. And here is a loss function to suppress the outliers effects, the impacts of the outliers. And finally, the object function can be derived. This is the LiDAR scan matching factor, and here's the IMU pre-integration factor. In this paper, we only use the middle LiDAR to do scan matching to provide the LiDAR odometry information, and the left and the right LiDAR is only applied to transform to the middle LiDAR to enhance the FOV of the puncture map to increase the density, also increase the density of the map. For more detail, readers are recommend to read our paper here. And the second part is we can do the errors detection based on a generated map. How we do it? Actually, this is also based on last year's IONGS Plus paper. Here is the puncture. For example, assume we have a satellite here. Actually, we can from the intuitively we can find actually it's blocked. But for the computer, how we do it? Finally, we draw a long side and distribute several points, searching point here. Long side is determined based on the elevation angle of the satellite and the azimuth angle. And then we define a searching distance, and then we can search through this line to find out if there are some punctures located inside here. It means it's blocked. But from in this searching point, it's not blocked. The points inside the circle is almost zero. It's smaller than threshold, so it will go to next point and search it until to here. Some punctures are located inside the circle. It means this long side is blocked by a puncture, and therefore we can find it's a long side satellite. Okay, here's the example in our data set. Last one is after we apply the NLOS exclusion, we can do the RTK positioning. Here is the major principle, and we are going to brief how this is done, this is achieved. And in here we have measurement from U blocks. We first do the Pseudorange modeling, carry phase modeling. We can get the Pseudorange from here's from the lower receiver. Here's the reference station, Pseudorange and carry phase, and we can do the double difference. Oh, sorry, this one is the master satellite. Master satellite, and this is the selected satellite here. W represents the master satellite, and S represents the satellite you want to apply double difference. Here's the measurement from the reference station. It's represented by this. Okay, and then we can do a double difference to get the double difference Pseudorange and double difference carry phase. And finally, we can estimate the first solution. Then we can do ambiguity resolution using LAMBDA. Okay, LAMBDA. It's a very typical modeling of the Pseudorange measurement. It includes here's the Pseudorange, and here's the expected range, and here's the clock bias, and here it's in spheric errors and it's chop spheric errors. And a very similar modeling is applied to the carrier phase. However, here is the range measurement. However, we got another unknown variable, it's the ambiguity, to be estimated before we can absolutely using the carrier phase for the GNSS-RTK positioning. Okay, to use the carrier phase measurement, the ambiguity need to be resolved. After correctly resolved, we can get a fixed solution. This is actually what we expected even in urban chaos. And actually, this is based on the RTK lib. The model is based on RTK lib. And then after you get the double difference measurement, we can get the weighting based on the signal loss ratio and the elevation. And then we get the geometry matrix, and we can do the least square weighted least square operation to get the state. Here's the position. Here is a double difference, the integer ambiguity for first satellite, second, and the M-1 satellite. Okay, finally, what do we get after the first solution? After we do the first solution estimation using weighted square, is the position and the fraud ambiguity, double difference ambiguity, and the corresponding covariance matrix. Okay, finally, we can do the ambiguity resolution using LAMBDA algorithm. In here, we're using the position and the ambiguity and corresponding covariance, and the geometry matrix can be denoted like this. And first, we can do the Z transform. This is a very typical LAMBDA process. Okay, readers can refer to this one, and we can do the ambiguity searching and inverse Z transform, and finally, we can ensure least square solution can be obtained. If the geometry is good enough, you can get the fixed solution, and also it determined based on the geometry and the measurement quality, whether you can get a fixed solution. Okay, and the implementation of the RTK positioning is based on previous work. This is open source framework, open source presented in ICORA 2021. It's presented this year. Actually, if you are very interested in this framework, it's a vector graph-based GNS positioning and the GNS-RTK positioning framework. If you are interested, feel free to try our code. We also provide some data sets for your reference. And here is the vector graph for the GNS positioning. It's the integration of the Pseudorange and the Doppler velocity. This is for the single receiver based GNS positioning. And then here is the framework vector graph for the GNS-RTK. In here is the double difference measurement, and in here is the Doppler velocity factor. Here's the state you want to estimate. Actually, let's two vector graph, typical vector graph for GNS positioning. This is for GNS-RTK. Okay, the last step, how we can using the fixed solution to correct the map. Actually, after we get the fixed solution, we can use it to correct the map. And here's the laser inertial. Okay, finally we can derive the cost function like this. Here's the LiDAR inertial, and here's the GNS-RTK positioning. And finally, you can use optimize this to correct the map. And here's the residual derivation from a laser inertial integration. Actually, this is also based on previous here. And here's the residual from GNS-RTK, the GNS-RTK positioning, and it's the expected one. And finally, we also apply a cost function, loss function to resist the outline, potential outlines. Okay, experiment is done in this kind of scenario using our experiment vehicle. We got some tall trees and tall buildings, scenario trajectory like this. And we compare three methods. The first one is GNSS-RTK. The second one is the U-box solution from the commercial side. And this is the proposed method. We do the NLOS exclusion and then we can calculate the GNSS-RTK positioning. In here, we find we get 17 satellites, and after we do the exclusion, the mean satellite number is like 50, and the mean error decrease from 6 using RTK to 2, and finally we improve from 2.4 to 1.9, and the fixed rate is slightly increased to 1.6. However, let's say due to why the fixed rate is still very low, because after we exclude and loss, the geometry gets very poor. It's still pretty hard to get a fixed solution. That's why our improvement in the fixed rate is quite limited. Here's the errors and the corresponding excluded non-linear site. Typically, we exclude maximum of 4 satellites and minimum of 1 satellite in this kind of scenario. The foliage can also cause incorrect GNSS errors with detection. And here we can find because some signal can directly be reflected through a tree. But for punctual detection, punctual-based detection, it can cause some incorrect detection. We also think this is also a question we need to study in future work. Conclusion. This paper proposed a switch LiDAR aided GNSS NLOS exclusion for GNSS-RTK, positioned by reconstructing the surrounding map using onboard switch LiDAR, and slightly improved accuracy and fixed rate is obtained. We can look into the fixed rate improvement, but very limited because after NLOS exclusion, the geometry is very poor. Our very previous work also found a very similar phenomenon. If we exclude too many satellites, the position results can get worse. And our future work is going to improve LiDAR features to constraint. We try to improve geometry after we exclude and loss. The concept is like in urban Kenyas, we got some trees, we got some buildings, and the buildings can block the signals. Therefore, we get non-linear side signals here. The blue one is the linear side. Okay, after we exclude, we detect the non-linear side. For example, the scenario can like this. After exclude all the non-linear side, we only get 5 healthy line side measurement. What can we do? We get such kind of poor geometry. It's pretty hard to get a fixed solution because of the poor geometry. Our idea is like, is it possible we apply the surrounding low rising environment features, for example, detected by the LiDAR, to constrict the state of a GNSS receiver to improve geometry. For example, in here, we exclude those satellites, but we can use low-lying geometries here. It's very complementary. It's similar, like it looks like these are auxiliary satellites. This is our next work. We are going to improve low-lying features to improve geometry. We think this can essentially improve geometry, combining all the long side measurement and the low-lying features to improve geometry. Okay, thank you for watching our presentation. Thank you. If you have any questions, please feel free to send email to us. Thank you. Bye.